For a naturally aspirated engine, performance is governed by a hard physical limit, atmospheric pressure. The engine can only pull in the amount of oxygen that the surrounding air provides, which strictly caps the power it can generate. In 1885, Gottlieb Daimler patented a workaround. He introduced the Turbocharger, a mechanical, gear-driven pump designed to forcefully compress and shove extra air into the cylinders. While the supercharger increases power, it does so at a cost. Because it is connected directly to the engine via a belt or gears, it is parasitic. It must steal a portion of the engine's rotational force just to generate its boost. For engineers, the challenge was to find a way to pressurize the intake without sacrificing the very power they were trying to increase. In 1905, Swiss engineer Alfred Bucci realized that the solution was already being blown out of the tailpipe. He patented a system that powered the intake by capturing the engine's wasted, expanding exhaust gases. The mechanics are straightforward. Hot exhaust spins a turbine wheel, which connects to a compressor wheel on the same shaft. This compressor draws in outside air and forces it into the engine under pressure. This became critical in the rarefied air of high-altitude flight. During World War II, turbochargers allowed bombers like the B-17 to restore their sea-level power in environments where naturally aspirated engines simply couldn't breathe. But relying on exhaust creates a new problem. When you press the accelerator, the engine is momentarily unresponsive because the turbine is stationary. It takes time for the exhaust pressure to build and overcome the physical inertia of the heavy metal wheels. This delay is known as turbo lag. By choosing free energy from the exhaust, engineers inherited an unpredictable gap between the driver's demand and the engine's response. To fight the lag, engineers first looked at the weight of the hardware. A smaller, lighter turbine wheel has less inertia, meaning it requires less exhaust pressure to start spinning. This logic created the parallel twin turbo setup. The exhaust stream is split in half to feed two smaller, identically matched turbochargers that can spool up much faster than a single large unit. Parallel setups bridge the gap, but they struggle with volume. Small turbos provide great response at low engine speeds, but they cannot push enough air to sustain high RPM power. The 1986 Porsche 959 introduced a more complex solution, sequential turbocharging. It used a tiny primary turbo for immediate low-speed boost, then transitioned to a massive secondary turbo to handle the workload at high speeds. These multi-turbo systems smoothed out the power delivery, but they required immense plumbing and heavy hardware, and they still relied on exhaust gas to do the heavy lifting. The next challenge was to make a single turbocharger adapt its own physical dimensions to match the engine's RPM. This is the variable geometry turbocharger. It surrounds the turbine wheel with a ring of adjustable vanes that can pivot to change the angle and speed of the incoming gas. At low speeds, the vanes close to create a narrow nozzle. This forcefully accelerates the small volume of exhaust gas, making it strike the turbine with enough velocity to spin it up instantly. As engine speed increases, the vanes open up. This allows a massive volume of exhaust to flow through the turbine housing without causing back pressure or choking the engine. Variable geometry is efficient, but it has a thermal ceiling. The moving vanes are delicate, and in the high heat environment of a gasoline exhaust stream, we are often prone to mechanical failure. To truly eliminate the delay, engineers had to spin the turbine without waiting for the exhaust gas to arrive. The electrically assisted turbocharger, or EET, does exactly that. It places a high-voltage electric motor integrated directly onto the shaft that connects the compressor and the turbine. The moment the driver touches the accelerator, the motor jolts the shaft to over 100,000 RPM. This happens in milliseconds, providing boost long before the first pulses of exhaust reach the turbine. Once the engine catches up, the electric motor turns off. The building exhaust pressure takes over, sustaining the rotation of the shaft for the remainder of the acceleration. By decoupling the initial spin from the engine's exhaust flow, engineers finally separated forced induction from the delay of fluid dynamics. The result is a machine that pairs the efficiency of a turbocharger with the immediate, linear response of a naturally aspirated engine. This technology was refined in the high-pressure environment of Formula One. Now it has reached the street in vehicles like the Porsche 911 GTS, where electric assistance manages the transition between idle and full boost. We have moved from the heavy, belt-driven pumps of the 19th century to systems that anticipate the driver's intent with electrical precision. The century-long effort to eliminate turbo lag shows that once mechanical ingenuity reaches its physical limits, the solution often requires looking outside the machine, replacing the pressure of exhaust gas with the precision of a high-speed motor.